Okay, here is your view on tension members. The first thing you need to remember is that the goal is always to try to have your capacity phi t p n greater than or equal to your demand pu. In order to do that, you guys know how to calculate demands from your structural analysis course. We're going to focus a little bit more on the capacity side. So we need to think of, okay, what are some ways that tension members can fail? Well, let's list some different failure modes or limit states. Limit states right there. So one that we've talked about in class is the yield limit state, YLS. Another one is the rupture limit state. We abbreviate it RLS. Another is the block shear limit state. There's no fancy abbreviation for that one. And the other is a general serviceability check for slenderness. So I'd like to talk about each one of these briefly and then go on to a rough design method for tension members. So the yield limit state is what we'll talk about first. This we're going to use to check to make sure the tension member does not yield over the gross cross section. So the yield limit state, Pn is going to be equal to Fy Ag, where Fy is the yield stress and Ag is the gross cross-sectional area. So if you had a tension member that was, a simple tension member, say this was a plate that was 3 inches wide and it had a thickness of 1 inch, what is Ag? Well, it's just going to be equal to 3 inches times 1 inch, which is 3 inches squared. And that's how you calculate it. You don't account for bolt holes in the yielding limit state. You just use the gross cross-sectional area. Do not use the net cross-sectional area here. So that's how you calculate it. A lot of times they give you L shapes or W shapes or other shapes, and you can look up the gross cross-sectional area in table 1- or in chapter 1 of the manual. So let's move on and talk about the rupture limit state. This one is a little bit different in that you actually have to account for the area. Oh, and another thing that I should mention, what is phi in the yielding limit state? It's 0.9 because the yielding limit state is not a brittle failure, so we don't penalize our capacity as much. So in the rupture limit state, we can just start by saying phi, it's brittle, so we know phi is going to be less. They use 0.75. And in the rupture limit state, the formula for Pn is equal to the effective area times the ultimate stress of your steel. So the effective net area is the big deal in this section, right? This is what we've spent a lot of time talking about. So let me just talk about it again really quick. So if you have, once again, a plate and you have some bolt holes, say we have a pattern, something like this. So you already know how to calculate the gross cross-sectional area, right? So the first thing we need to do is we need to calculate the net area in order to use it to get the effective area. So we can say the area net equals the area gross minus the area of the holes, right? So let me just draw a cross-section for you. We're going to say, I'm going to draw this cross-section right here. It will look something like this, where you have a bolt hole here and you have a bolt hole here. So if they tell you that the bolts are 3/4 inch bolts, then how do you use that 3/4 inch to calculate the diameter of the hole? Well, what you have to do is they always make holes 1/16 bigger than the bolt, so the bolt will always fit and it won't get stuck. So you add 1/16 inch for a fit, and then to be conservative, they say we're going to add another 1/16 of an inch, just in case maybe the bolt hole was cut a little bit too big, or maybe the material was heated too much and so it's not as strong, or there could be a number of different reasons, but to be conservative, it's always an additional 1/16. So total, you always add 1/8 of an inch to your bolt diameter, not your bolt hole diameter. You add 1/8 of an inch to your bolt diameter. So here we would have, you know how to calculate AG, and then the area of the hole would be the 3/4 of an inch plus 1/8. That would be the diameter, right? And then you'd have to multiply by the thickness of the part, if this would be T. And then since there's 2 bolt holes, we would multiply that whole thing by 2. That would give you your net cross-sectional area. Now, in order to calculate your effective cross-sectional area, AE is equal to U times AN, where U is the shear lag factor. The shear lag factor accounts for a phenomenon where the tensile stress is not taken by the entire cross-section at given points. So let me illustrate this. Imagine a gusset plate with a tension member on it that looks something like, let me try to draw this in 3D actually. This would be helpful. So say we have an L shape. It's going to look something like this. I hope you guys can see how that's an L shape. And we're going to say it's attached to a plate by, well, let's make this plate a little bit longer. We're going to say it's attached to a plate with some bolts right here. And we're pulling on it in this direction. Now the force in these bolts is going to travel through the member, and it's slowly, the cross-sectional area will get more effective. So at this bolt, these bolts back here, we're only going to have this much of the cross-section being effective. And as you move out the bolt hole pattern, this force goes something like this. So more and more of the cross-section starts becoming effective. So at this line of bolts right here, you're actually only going to have, you know, some form, about this much of your cross-section resisting your tensile force. So that tells us that our shear lag factor will always be less than 1, because it's accounting for not all of your cross-sectional area is resisting the force at the point that you're calculating. So that's what the shear lag factor is. The way you calculate it is you go into chapter D in your manual, and let me just check that I'm not lying to you really quick. You go into chapter D. It's on page 16.1-28. And it gives you different ways to calculate your shear lag factor. This video is not supposed to be super long, so I'm not going to go into detail on how to calculate the shear lag factor, but know that there is formulas for it and a table for it. So the other thing that we need to talk about is, what if you have staggered bolts? So you have bolts maybe something like this, where they're staggered. Well, what they do is you say, okay, there's multiple ways that this can fail, right? We know that it could fail on this line, or it could fail on this line. It could fail in other lines, but these are usually the two critical cases. So we're going to say it's attached on this side. Oh, that's terrible. We're going to say that it's attached like this and that. We have a tension force like that. Okay, so how would you calculate the cross-sectional area in this case? Well, in this case, the diagonal portion right here is what gives us trouble. You can calculate the areas here and here. You guys have the ability to do that. You do it the same way that you'd calculate the net area, but this one is a little bit different. So what AISC says is they just give you a little fudge factor. They say it's S squared over, I believe, 4G. Let me look that up really quick. Yeah, S squared over 4G, where G is this distance, the gauge, and S is the pitch. Oh, sorry, I drew that wrong. S is the pitch. So you add one of these times the thickness for every diagonal. So in this case, there's only one diagonal. You would add 1 S squared over 4G. You'd calculate AG as normal. Then you subtract the diameter of the bolt holes. In this case, there would be 2 bolt hole diameters to subtract. So hole times the thickness. And then you would have to add, because we're saying the diagonal area gives you a little bit of a bonus. You have to add S squared over 4G times the thickness. So that's how you account for that. If this was an L shape, you'd have to unfold it, and we can talk about that some other time if you guys have questions on that. So those are 2 limit states. The third limit state is block shear. And block shear has to do with a combination of shearing and tension. So now let me draw this a little bit bigger for you. So if we have something like this, we have several different ways that this can break. We've talked about 2 already. Let's think of some other ways. Well, we know that this line right here could break. So that's one. You can just imagine that this section stays where it is, and the rest of it, just the rest of the tension member pulls off. You can imagine that. Then you have just the opposite. I'll do it in blue, where you have failure along this blue dashed line. And then these blue sections stay, and the rest of the tension member pulls off. There is a third option along this green dashed line that goes all the way to there. That could also be, you can imagine this area in green that stays and the rest of it pulls off. So you're imagining all these different possible ways of a shear area and a tension area that can break to cause failure. We call this block shear. Now, formulas for block shear are given in Chapter J. This is somewhat confusing for people because they say, oh, why isn't it in Chapter D for tension members? Well, Chapter J is for connection design, so they consider block shear a limit state for connection design. But you will have to check it because your tension member will have to be connected to something. So the formulas are listed in Chapter J, but basically what you're going to be doing is you're going to be finding, so let's take these blue areas, right? What would be the area that is getting sheared? Well, let me bold it for you a little bit. This area, and this area, along with that side, that part will be under shear. The part that will be under tension, let me bold it now in blue, I'll bold it even more, is this section right here. Notice how I did not include the bolt holes. You do not include the area of the bolt holes when you are calculating your gross or your net shear area. Now, when you calculate your gross shear area, you would actually include them and you'd get all of this area that's here for the shear. You never calculate a gross tension area. You never use that in Chapter J. You only use the net tension area. Sorry, I think I said that wrong. You don't ever calculate a gross tension area. You only use the net tension area in your calculations. So once again, you'll have to find the area of these, multiply them by FU or FY, respectively, based upon the equations, and you can come up with your capacity for block shear. Now, there is one other limit state that's a serviceability limit state, and that is slenderness. So slenderness is a much more simple check. It is, you just take the length of your member, divide it by the least radius of gyration, and that has to be less than or equal to 300. For built-up members, the distance between connectors divided by Ri has to be less than or equal to 300. So be careful, they're just slightly different. This is for built-up members, and this is for single members. Okay, so the other thing that I just want to quickly run through is how a design process might look. A design process, you would use the table in the tension member chapter of the manual, and you would calculate what's my PU. So let's put design. What is PU? Question mark. You'd calculate PU, and then you'd go into the table and you'd pick one that has a capacity for the yielding limit state that is greater than or equal to PU. And then you'd try that shape. Now, you don't know that that shape will work in the other limit states, so now you'd have to check other limit states. You could also calculate your required net area, your required effective area. That's a little, in my opinion, that's a little bit more tricky, but you can do that too. It works just fine. There's multiple approaches to design. In the end, you just need to make sure that your shape satisfies all of the limit states. And there's more to this. I know it's not just cake, but if you have any questions, please come talk to us, and I hope that you guys can understand tension members well.